Okay, so thank you all for joining this week's Applied PD seminar at the University of Washington. It is my pleasure to introduce today's speaker, Maxim Olshanii. Dr. Olshanii got his PhD in 1992 from the Institute of Spectroscopy in Moscow. After postdoctoral stays at Harvard and the ENS in Paris, he became a faculty member at the University of Southern California, switching to the University of Massachusetts, Boston in 2007, where he's been since then. He's a fellow of the AMS. His research interests span many areas, mostly in atomic physics, with an emphasis on cold atoms and integrability, both quantum and classical. He's got a very long title today, which I will let him read himself. So here, so we'll get the talk started. Thank you, Dr. Olshanii.
Yeah, thank you so much. And just one thing, I would be delighted to be a fellow of AMS, but I'm a fellow of APS.
Oh, I'm sorry.
American Physical Society. But this is in the future. No, this is in the future. No, that's a Freudian slip. Yeah, I want to be one. Right, and so indeed, thank you so much for coming. And the title is indeed long because the talk is about one particular conundrum that emerged two years ago and emerged experimentally, and for a year or so nobody knew what to do with it, and the resolution was done through the long chain of maps between various known things, and thus a long title because the title reflects the maps. But I will let me start from the actual conundrum, and then we'll see what the rest of the ingredients do to us. And so first comes, as usual in physics, the phenomenon. And the phenomenon happened, was measured at the École Normale Supérieure in Paris in the group of Jean Dalibard, and the phenomenon is literally this. Okay, so imagine you have a system called atoms, so those are cold bosons, which are covered by a two-dimensional nonlinear Schrödinger equation, or two-dimensional Gross-Pitaevskii equation. So what you can do, you can do many different things with them, and in particular, what you can do is experimentally, you can create a corral, like a fence, of any shape, and then release atoms from this corral to a harmonic trap. And the expectation was what's going to happen was very low. The expectation was that after all, it's not a solvable system. It's just a generic system. So two-dimensional nonlinear Schrödinger equation. It should thermalize somehow. So it should increase its entropy. And when you start from, you can see my cursor, right? Can you see my? Yeah. Okay, so when you start from a square and then time propagated, and time goes from the left to the right, and then from the top to bottom. When time propagated, you would expect that eventually, so this loss of rotational symmetry will reflect itself in round shapes. So you have to end up with an information less than the information started, or with an entropy higher. And indeed, for the most shapes, actually for almost all shapes that they tried this experiment, this was exactly what was happening. So you start, again, it's a two-dimensional Gross-Pitaevskii equation. You start with a flat bottom corral of, say, square or hexagonal or pentagonal shape. So then you remove the walls of this corral and simultaneously create a harmonic confinement around it. And the system evolves. For some time it remembers it used to be a square, but then by the end of the day it's just perfectly round. And this is something what we who work on the interface between cold atoms and thermodynamics and PDEs. This is something that we completely expect. But then, to complete the series, they decided to try triangle. And what happened with the triangle is that triangle didn't thermalize at all. So instead it was breathing. So you create a triangle. So then it becomes a hexagon, then it goes upside down, then it becomes a hexagon, it goes upside down again. And this was repeating for many, many periods with no apparent end. And the moment many of us, including myself, saw it, we lost sleep. I mean, so we didn't actually. It was so stunning and so unexpected that that many of us just started thinking about it, and the solution was found eventually. Oh yes, and by the way, this is a movie of what is happening. So this is how it breathes. So that's a movie of how it's happening. And the solution was found, and I keep saying that, I mean, this paper by Shi Gao and Zhai from Tsinghua University, this paper could have had just one reference to the original experiment. It is so original and so out of the blue. I mean, I couldn't imagine it was possible. And so the first question to answer here is the following question. So what is the question, the answer to which is a triangle? And so indeed, I mean, so apparently triangle shape has some properties other shapes don't. And the answer is this. So the answer to the question, the answer to this question about the question is this. So for what polygon the following is true: any intersection of two homothetic copies of it subsequently parallelly shifted is itself homothetic to it. And so, I mean, it's a long question. Let me show you what I mean. So take a circle, take a disk, create a copy of this disk, rescale it, and superimpose them. So intersection won't be homothetic to the original disk. However, if you take a triangle, create a copy of it, rescale it, superimpose them. So the intersection is homothetic to the original triangle. And this, in fact, this is a property which is unique to triangles, equilateral or not. We'll discuss how important the being equilateral is. So for any triangle, this is true. And so why is it important? It is important because what the Tsinghua group realized is that the solution to the problem lies, in fact, in free motion of free particles in a harmonic trap. And they posed the following question. And the question is this. So imagine that you have an initial phase space, like coordinate and velocity distribution of non-interacting particles, time propagated, under which conditions the time evolution of the mean velocity, local mean velocity, and density will be governed by by a set of hydrodynamical equations exactly. And mind you, this exactly doesn't happen even for ideal gases. So we keep saying that the local velocity distribution is a Maxwell distribution, but not quite. It is an approximation. So there is a truncation of BBK, YG, RRQ, whatnot, that actually typically makes hydrodynamics inexact. And they wanted to have the Euler's equation. So the material derivative of the velocity equals a gradient of some local energy, or rather chemical potential, Gibbs energy, and the harmonic force exact. And so I probably won't go through the whole derivation because I want to stress one more point, which is closer to the interests of the audience. But there are two questions. So question number one. Are there any initial conditions under which the energy per particle at a point is a function of the density alone. So this is the reformulation of the first question, and this is just one part of the first question. And the second question is yes, and the second question I'll get to it. And so what people started thinking about is well, maybe if you start from initial distribution, which is the tensor product of two shapes with a flat top, so maybe this shape will produce an energy that is only a function of the density, which simply means that the shape of the velocity distribution remains the same at every point in space-time. So this is what we're looking for. So we sit at a particular point in space, at a particular point of time. We look at the velocity distribution. So what we want it to be is a particular function of velocity, which is a rescaled version of the same shape, like maybe a Maxwell distribution, but maybe not. And so you start from a tensor product of two disks. One is in real space, one in the velocity space. There's a technical minus sign. You construct the time evolution in a harmonic trap, which is just a linear transformation of the coordinates and velocities, and we'll get something which is not entirely a function of the density, because it's a different shape, so in different points of space and time. But when you start with two triangles, triangle in real space, triangle in velocity space, and the tensor product of them gives you the initial distribution. Time evolve, so time evolution, mind you, includes rescaling and rescalings and shifts and nothing else. The result is the very same triangle. So your velocity distribution remains self-similar at all space-time point. Energy indeed becomes a function of the density. You can compute the chemical potential, and this chemical potential it's a new equation of state. It's not a chemical potential of free fermions. It's not a chemical potential of free bosons. It's something new. So this is a new state of matter, and so the next what they did, and this is the most natural step, is that take the chemical potential for these abstract particles and replace h bar there by fictitious h bar, which we should construct in order for this chemical potential to reproduce the chemical potential of a free of a cold interacting Bose gas, which include which is, and chemical potential for a Bose gas is always linearly proportional to the density, and this is precisely what you get in this problem. Also, linear dependence on the density, and what you get for free is a subset of solutions, exact solutions, for hydrodynamical equations for an interacting Bose gas. So in short, you got a partial map between interacting bosons and free particles. I mean, sometimes I call them fermions for a reason, but and free particles. And this map is entirely new, and it gives you a subset of exact solutions of the hydrodynamical equations in 2 dimensions. And more to the point, the solution perfectly reproduces the ENS experiment. So question number 2, in fact, is, so in principle, you can try any triangle. So any triangle will have this magical shape. So assume assume energy as a function of density alone is satisfied. I mean, is it sufficient for the existence of hydrodynamics? And it turns out that there's a second condition, that also, never mind, pressure tensor must be isotropic, and this is true only for equilateral triangles, and it was a conundrum it was a puzzle for some time, because experimentally Jean de Lebar also tried non-equilateral triangles, and there was nothing there. They were perfectly thermalizing. So it's equilateral triangles alone, and so at this very point you can say, okay, so this is done. And indeed it is. Okay, so what people who didn't make the original discovery do. So they do two things. Okay, so and I'll do both. They try to reinterpret a great result in some other terms to gain a new angle. And this is the first half of my presentation of our own results. And the second thing is to go back and notice that there's still not a mathematical problem, but how this phenomenon poses a new fundamental problem, or at least fundamental in our minds. And this is precisely what this work is about. I would say it's a brilliant follow-up. But the actual discovery of this map is indeed the group from Tsinghua. So and I'm done with the introduction, and so now let me show you what we did with the thing. So we start from afar. So we start from something most of you we start from. Actually, we start from an old paper by Chandrasekhar, which is called "On the Decay of Plane Shock Waves," and it was done in 1943 in the middle of the Second World War. And in fact, this paper is a follow-up for another one, which is called "An Optimal Height of the Bursting of the 105 millimeter shell." And this was really what his interest was at the time. And only later on, there was a paper which was called "On the Decay of Plane Shock Waves." So in short, and so the paper is long and it's about actual hydrodynamics, but in short, so his mathematical discovery is this: we take something most of you know by heart, the nonlinear transport equation. That is elementary, explicitly solvable, and you of course know that what it describes is a motion of free particles with some initial velocities, and it describes the evolution of the velocity field as a function of coordinate and time. And you probably know that the solution doesn't exist forever. So at some point in time, there will be a catastrophe when you get several velocity classes at the same time, and then you would need an underlying theory to regularize this catastrophe. And in this case, the underlying theory is just Liouville's equation for these particles. I mean, they could continue through without knowing of any catastrophe. But you need to know behind the nonlinear transport that dies at this point. You need to know a bigger underlying theory, and this theme will go throughout my talk, and it will reappear several times. And this is the catastrophe. This is my favorite book on catastrophes, written by Jan Stewart, British author, written in French, never translated to English. I'll work with it. And he recently also co-edited the Courant and Robbins What is Mathematics, and so he's a great writer. And so wait just a second, let me return to the anyway, so there is this general solution. And so what among other things Chandrasekhar found in this very influential paper is that there is one solution that sticks out, and the solution is simply zero T. So if you take this solution, and so what happens is that there's a like in Hubble's law. So the velocity is linearly proportional to the distance, and then the velocity field becomes shallower and shallower, so less steep and less steep with time, because particles move away, and this is normal. This is what happens with the Hubble expansion. But what we're going to argue is that what is realized in this experiment with triangles or the edge of them is nothing else but the Chandrasekhar's solution for the nonlinear transport equation. But there is a long map between between the nonlinear transport and BEC and the nonlinear and the two-dimensional nonlinear Schrodinger equation. So we need to get through this map. Okay, so this is this, and actually I should correct these slides. Right, so the first map that happens, it was discovered by Bogdan Damski. Indeed, it turns out that if your initial density in your hydrodynamical equations is proportional to the velocity, to the square of the velocity with a particular coefficient, so then there's an exact map between nonlinear transport equation, which is easy to solve, and the one-dimensional hydrodynamics for both gases. So again, this is the continuity equation, this is Euler's equation, and the force field is a gradient of is proportional to the gradient of the density. There's another map that I won't. There's a map between no trap and trapped. So don't forget that there's also a trap in the game. This is a great paper that discovers an additional symmetry equivalent to a two-dimensional Lorentz symmetry for two-dimensional Gross-Pitaevskii equations. I won't describe the map. It's a long story. It connects the ends. So it connects no trap to a trap situation. So we connect so we connect one with another, and start comparing. And what we're seeing is this. So red is the exact solution of the hydrodynamical equations, and this line is indeed the Chandrasekhar solution to the nonlinear transport equation, mapped to the one-dimensional nonlinear Schrodinger equation, mapped to a two-dimensional equation because we are working with a sharp straight edge of a triangle, mapped to a solution in traps, and so after all this map, we get this beautiful correspondence, and of course this paper is a follow-up, but nonetheless, to see, we were very pleased to see a connection with something that was known in an entirely different area, and in the nonlinear transport, and also in standard Gross-Pitaevskii. So this is one result. This is one result, and we published it. And so now we started thinking about the following. Okay, so the question is this. I mean, so imagine. So after all, I mean, so when you start in the beginning, so you have this triangle shape. This triangle shape has an infinitely sharp edge, and at this point, hydrodynamics doesn't know what to do with it. I mean, hydrodynamics needs. Hydrodynamics dies because there is a gradient of the density is involved. Gradient is infinite. There are infinite forces, and but Gross-Pitaevskii itself, it beautifully goes through. And the following analogy comes to our mind. Okay, so we take the breezer, and let's assume that the hydrodynamics is something that we know and control. Let's assume that hydrodynamics is something akin to the standard model of particles, and it works most of the time. But then it approaches the last 3 minutes before the big crunch. And what happens is that the density gets steeper and steeper, and then at some stage, it develops an infinite spatial derivative. So notice what happens just before this moment. So the edge, let's the bottom edge of this triangle, it moves towards the origin with a speed which is two speeds of light, two speeds of sound. So then in this region. So again, Gross-Pitaevskii knows what to do, but hydrodynamics doesn't. So we can get through it. And what we're seeing is that the velocity of the edge instantly changes its sign. And so definitely a dynamical symmetry, dynamical theory cannot reproduce it. So it's at an instant, and in fact, this is last time when you saw a flying saucers. I mean, that is flying saucer. That's precisely what they do. I mean, they fly with some speed and then instantly change the direction of their velocity. But again, I mean, underlying Gross-Pitaevskii beautifully regularizes this singularity, and after we regularized it, and in fact, what happens is that we have to restart the hydrodynamic equations with a new initial conditions, and somebody needs to tell the hydrodynamics with what initial conditions to restart. And so in our case, it is Gross-Pitaevskii that does it, and that's this. Okay, so two-dimensional Gross-Pitaevskii introp. It informs the hydrodynamics how to restart after catastrophe. And so in our universe, probably it is the quantum gravity that is regular and that survives the big crunch, big bang transition. And the question, naive question we have is, so in terms of the quantum gravity, the question is, do we need to know the quantum gravity to restart the standard model after the big crunch, big bang? Or there's a unique way it can restart even without knowing what's inside? And in the hydrodynamical Gross-Pitaevskii case, again, I mean, do we need to know the Gross-Pitaevskii equation in order to restart hydrodynamical evolution? And there's an analog of this question in the standard hydrodynamics with ideal gases, with temperatures and stuff. So there is a crucial difference between one-dimensional and multi-dimensional shock waves. So for one-dimensional shock waves in air, okay, so we're not talking about gases, in air, conservation laws alone are sufficient to connect the gas dynamics before and after the shock wave front. So one doesn't need to know the viscosity of the gas in order to get from one side to another. And in higher dimensions, one needs to know the actual properties of the gas, like viscosity inside the shock wave front. And we don't know which class this problem belongs to. So we don't know if this scenario, this hydrodynamic scenario we're seeing, unique. So these are all the questions that they posed. So do we need to know the quantum gravity to propagate standard model through the big crunch, big bang? And here's my attempt to reformulate the problem. And whoever is interested, I'll send this handout out. And so the question is literally this. So we start from I diluted it to a one-dimensional problem, so we don't need to worry about harmonic traps and anything. So this is the simplest possible way to formulate the question I have. So start from a one-dimensional nonlinear Schrödinger equation, or one-dimensional Gross-Pitaevskii equation. So now we have time dependence, we have kinetic energy, and so we have the pressure term. Start from the following initial condition, which is, from the point of Gross-Pitaevskii, it's an absolutely normal initial condition. So it's 0 for z greater than 0, and it's a tangent. I don't remember why I have -1 and -z, but probably I had a reason. Yes, and then a hyperbolic tangent for z less than 0. And for those of you who don't know, this is also a stationary solution for the nonlinear Schrödinger when you have an infinitely high wall. Infinitely high wall, and this solution is propagating to the left, and so it is flat. There's a flat density almost all over the place, but then just next to the wall, the jump in density is regularized by the hyperbolic tangent, and is regularized on a length scale which is inaccessible to hydrodynamics, is so-called healing length. Okay, and so many of you know about the so-called Madelung transformation. So Madelung transformation literally this: interpret psi square as the density of some fictitious particles. Interpret the gradient of the argument of psi as a velocity field of the very same particles. Plug this expression for right now. Express psi through the density and velocity. Plug this expression back to the nonlinear Schrödinger. Compute the imaginary and real part, and it's not a mistake. So you should first compute the imaginary part, and then you compute the real part. When you compute imaginary part of this of the nonlinear Schrödinger with the Madelung substitution, you will get nothing else but the continuity equation, and you will get it exactly. So when you compute the real part of the nonlinear Schrödinger equation under Madelung substitution, you will almost get the Euler's equation, except there will be one term which will be small, with a small parameter of typical size on which the density changes versus so the so-called healing length that has many mathematical meanings, as compared to right, if you want a healing length, is the length scale associated with the chemical potential, as compared to a typical size over which density changes. So this is your hydrodynamical approximation. So under this approximation, for example, the transition that a hyperbolic Sech undergoes from a constant density to a zero density, the width of this transition will become zero. And so we neglect terms of that order, the terms that involve a second derivative of the density with respect to space, and we get an Euler's equation. And so now we stay at this Euler's equation, and we pose the following question. So consider an initial condition. So under which no, not the initial condition. Just a second. No. Right. Okay. So let me say this way. So consider the physical the following initial condition, which is at the moment mathematically is not very sound. So there's an infinite jump in density. So density is n0 for z less than 0. It is 0 for z greater than 0. And then the velocity is 0 in the beginning, and then it is undetermined with the density is 0. As such, mathematically, this initial condition is bad. I mean, again, we don't know how to propagate from it. However, we can take the Damski-Chandrasekhar's shockwave solution that was mapped from the Chandrasekhar solution for the nonlinear transport equation. So consider it for t greater than 0. Okay, so for t greater than 0, this set corresponds to a beautiful. So it beautifully solves the hydrodynamical equations. So when take t, positive t, and move it towards 0. So this solution will converge to this kind of to this initial condition with an infinite step. And so the question we pose is this: so is Damski-Chandrasekhar is the only solution at t greater than 0 that converges to a step when we trace back the time to t equals 0, and it converges to a step in the density? And if it is the only one, then the answer to the actual question posed no. And the actual question posed was that do we need to know the underlying more exact theory, which is the nonlinear Schrödinger, in order to propagate hydrodynamic equations through a catastrophe point, in order to be able to restart the hydrodynamic equations with new initial conditions after the catastrophe. And I don't know if it's unique or not. And again, we're not experts, and I will gladly share this handout with everybody interested. And this is, in my mind, this is related to the question of existence and uniqueness. And I would be glad to. I I mean, we end here. This is where our level of incompetence reaches its maximum. All right, and interestingly, okay, right. Right, and I'm already arrived at the summary. Interesting. One must not really must not be too diligent in preparing talks. Oh yes, the summary is long. Okay, so in summary, so two things happened. So we reinterpreted the known Shi-Gao-Zhai solution for the triangle Gross-Pitaevskii breathers in terms of the Damski-Chandrasekhar shock wave, and something that Chandrasekhar discovered himself in 1943. Bogdan Damski did his work in about maybe 30 years ago. So it is all like old stories, and even the Pitaevskii Roche map is old, but it's nice to connect the two things. One is new, one is old. And the second is a more fundamental question. I mean, in what cases a theory that dies at one particular point can be restarted after the catastrophe without any external knowledge of physics just during at the moment of catastrophe, and in which cases this is not possible. And so in cosmological terms, I mean, do we really need to know quantum gravity in order to get from the Big Crunch to the Big Bang? And in our case, I mean, do we need to know Gross-Pitaevskii equation in order to pass through a point where this wavefront being moving with the speed of two speeds of sound upwards suddenly starts moving with two speeds of sound downwards, and of course it's a new initial condition, but maybe maybe just conservation laws or something, some simpler principles than the Gross-Pitaevskii would allow to predict this particular transitions through a catastrophe. And so this is the question I posed. And now the outlook. Triangle wasn't the only just a second. Oh yes, I mean this is precisely the question I posed. So right. So triangles are not the only ones for which breathing was observed. Also breathing was observed for disks. And so there are in fact two periodicities here. So one periodicity which is hard to see here because the frames are not in 1/7, but there is one periodicity with two periods of the trap over 7. 7 is an interesting number, and 7 doesn't appear often, and this is really this was really very, very interesting. And then there is another bigger periodicity with the period 2t, and of course you would tell me that yes, 2t is obvious. I mean, if it's periodic with 2t over 7, of course it will be periodic with 2t. What happened was that in reality the 2t over 7 was in the end in an approximate periodicity, and we've published we've published a paper about the 2T07. It is a combination of very interesting coincidences and maybe one general principle behind it. We still don't know, but in any case, I mean, it is approximate. It is very well. There are like 3 or 4 zeros of a particular function that force the reader to assume that the whole function is 0, and for a naked eye, I mean, it's probably 1 or 2% deviation. It's like nature was laughing at us. But be that it may, so 2T07 is not an exact periodicity of the motion. However, 2T is, and since January 2019, the question of the origin of the 2T periodicity of the two-dimensional Gross-Pitaevskii breezers is like a white snow desert of no idea at all. It's just amazing how nothing has been done in this direction, and I'm desperately trying since then, and I tried many things and I learned a lot, but I haven't moved the slightest bit to the resolution of this paradox. And so again, so for those who are interested, you have a two-dimensional nonlinear Schrodinger equation. You start with an initial condition, which is the ground state in a flat bottom circular corral. So you will get a flat density in the middle and some kind of a hyperbolic tangent at the edges to transition from a constant density to 0 density. And then you remove the corral and you add a harmonic drop. And the whole thing starts breathing, and it starts breathing with a period which is a 2T of the period of the drop. And again, if you are looking for an unsolvable problem, so here is the one, and I would be very glad if somebody can join me in this madness. And right, and so that's the support, and the gist of the talk again is a reinterpretation of the phenomenon of the triangle breezer in terms of Chandrasekhar solution he obtained in 1943. And I want to end, I hope the slide is still there, I want to end with my favorite quote from Sir Michael Berry. That's the group, and then I'll show you the group. So that's the quote. Nothing is ever discovered for the first time. And that's the group. So Dumfries Deschamps, he was a master student on the project. Jordi Torrens at the time, so he was an undergraduate student in the University of Barcelona. Marina Gonchenko, she's a mathematician in our collaboration. Vanya Dunka is a postdoc, and Gregory Straharczyk is a researcher with the University Polytechnica di Catalunya. And thank you very much. It has been 38 minutes.